Okay, welcome. This is Eddie's class. We are still on exponential distribution, and today we'll be going through a very important property of an exponential distribution, and that is memoryless property. Now, let's start by recalling the previous example that we saw on the amount of time that a post of credit spends in saving customers. So in that example, we saw that the waiting time for the exponential distribution is an average equal to 4 minutes per customer, or in exponential form, we can write it in this way. This is what we saw in the previous example regarding exponential distribution, the waiting times. So now, think for instance that you are saving customers or you are receiving customers, and you have known that on average customers, let's say, arrives after every 1 minute, after every 2 minutes, after every 3 minutes or 4 minutes. Okay, now let's take an example that on average customers arrives after every 2 minutes. That's the average time. Okay, that on average you expect the customers to arrive after every 2 minutes. That is the average waiting time. Now, for instance, think that after saving the last customer, then 5 minutes has elapsed since saving the last customer. Now, what will be our expectation? The expectation will be that, under normal situation, we could think that if 5 minutes has gone since we have saved the last customer, then it's likely that within the coming few minutes, can be 1, 2, or 3, then we're gonna receive another customer. Okay, to put it clear, that if your average saving is, let's say, 2 minutes, and you have spent 5 minutes without receiving a customer, then under normal situation you could be thinking that in the next, let's say, a minute, in the next 2 minutes or 3 minutes, it's likely that the customer will be coming, given that you have been waiting for 5 minutes. That could be the expectation. Okay, that since an unusual long time or not has gone. Okay, so it will seem that more likely, you see here, that it's more likely for a customer to arrive within the next minute, because on average we save the customer for 2 minutes, then 5 minutes has gone without receiving any customer. So it will be more likely to think that in the next minute or in the next 2 minutes we'll have a new customer. So this is the situation or the way we think under normal situations. Okay, now, but with exponential distribution, this is not the case. This is not the case. Maybe the other example, think for instance you are registering students, for instance, for a particular course, and you know the registration rate that after every 1 minute a new student registers. Now, if you spend more than 10 minutes without seeing a student registering, you could be imagining that in the next 2 minutes, in the next 3 minutes, we could have seen the student registering. So that is the normal situation or the usual way. But with the exponential distribution, that's not the case. Now, how it is, let's see this peculiar property of exponential distribution. So what is saying that with the exponential distribution, this is not, it's not the case. You can see with the exponential distribution, this is not the case. When is the case? It says, and this is the point that slide, you can see from this point to this point, that additional time spent waiting for the next customer does not depend on how much time has already passed or elapsed with the last customer. Okay, additional time spent waiting for the next customer does not depend on how much time has gone since the last customer. Now this is what makes exponential distribution peculiar than the other distributions. That waiting time, okay, or waiting time does not depend on how much time has gone since the last customer has been saved. Okay? So if you keep adding some more minutes, that one will not change the probability for the next customer to arrive. Okay? That's why they are saying additional time, you can read from here, additional time spent in waiting. Okay? Time spent in waiting. The time spent in waiting for the next customer does not depend on how much time has already elapsed since the last customer. And this is what makes exponential distribution to have what we call a memoryless property. Okay? Waiting time is not dependent, does not depend on each other. Okay? The probability for waiting for 5 minutes, okay, that we have been waiting for 5 minutes, and then in the next 2 minutes maybe we could think that it would be likely that the new customer to come in. So the additional time, the 2 minutes to be added, given that you have been waiting for 5 minutes, does not depend on how much time has already gone since the last comer has been saved. So this is exponential distribution, and it is what we call a memoryless property of an exponential distribution. So this is the memoryless property. Now how is it? Let's see. Okay. Now here is just an example. Let me pick yes, this color. I think this one will be blue. We have probability of x greater than r plus t, given x greater than r will be equal to probability of x greater than how much? T. Now this mathematical expression right here is what it means by this statement right here. Okay? That additional time spent waiting for the next customer does not depend on how much time has gone since the last customer. Now let us see. X, remember, is our event of interest. That X is the time, the average time for saving the customer. Okay. Now X is greater than R plus T. R is the time you have been waiting. Okay. Let's say the time you have been waiting since saving the last customer. Let's say you have been waiting for 10 minutes after saving the last customer. Now this T is an additional time, okay, that I've been waiting for 10 minutes, that is R. Then it's likely that in the next 2 minutes I'm going to receive a new customer. So C, R is the time you've been waiting without saving, okay, for instance 10 minutes. And then T, what is it? T, this one, is the additional time for you to expect receiving a new customer. That I have been waiting for 5 minutes, then in the next minute I'm going to receive a new customer. I think it's clear the difference of these letters. Okay, that I have been waiting for 5 minutes, it is this one here. Then in the next 2 minutes I'm going to receive a new customer. Okay, so time you have been waiting, time you expect to receive some customers. So this is the probability of R plus T, given that X greater than R. So the probability for waiting for addition of time T, given that you have been waiting for time how much? Time R. That's the meaning. The probability that a new customer will arrive at time T, given that this much has elapsed since saving the last customer. So what is this question trying to say? The probability that of waiting for having additional time, given that you've been waiting for time r, will be the same as the probability of time t. Okay, I will illustrate it more. For all r greater than 0 and t greater than how much? 0. Here's an example to simplify, or to just to describe what does it mean by that math. It says, if 5 minutes has elapsed since the last customer arrived, so think of this 5 minutes as r. Okay, has elapsed since the last customer arrived, then the probability that more than 1 minute will elapse before the next customer arrives. Okay, the probability that 1 minute will elapse before the next customer arrives is computed by using r equal to 5 and t equal to how much? To 1. So t is the probability you expect, the time which you expect the new customer to arrive, and the r is the time which has elapsed since serving the last customer. So if we come back to this equation down here, up here, so look down, we can substitute r for 5 for r and t and 1 for t. So it will be 5 plus 1, which makes it 6, greater or equal to x equal to 5, and this will be the same as the probability of x greater than how much? 1. That's the meaning. And it's what this sentence here says. Time does not depend on each other. So we can put it like this, that x greater than 5 plus 1, given that x is greater than 5, okay, r t, okay, will be equal to probability of x greater than how much? Greater than 1, which is our t. Okay, so of course this is a computation from the previous example. We shall see how to come up with this one. I'm going to give you an example. So this is the memoriness property, and it says additional time spent in waiting for the new customer does not depend on how much time has gone since serving the last customer. Here the key point and the most important thing to consider when you speak of the memoryless property. Okay, time for waiting a new customer does not depend on what has passed. Okay, if you are serving customers, because I'm giving an example of customers because you are speaking of customers, but it can be different things. Can be about electric lights, can be in terms of machinery, depending on the field of on which one is concerned with. So what is it saying? The next slide says exponential distribution is often used to model the longevity of an electric or mechanical device. Longevity of electric or mechanical devices, for instance, light bulbs, okay, can be modeled. Its longevity can be modeled by using exponential distributions. Okay, heaters, electrical heaters. You can model such distributions, maybe burning out, for instance, if it's your event of interest, burning out of an electric bulb, burning out of an electric heater, okay, can be modeled using exponential distribution. So here is another point to note when you speak of memoryless property of an exponential distribution, that the memoryless property says the knowledge of what has occurred in the past has no effect on the future probabilities. Meaning that if you go back to example for time customer arrival, that the knowledge of how many minutes has gone without receiving a customer has got no effect on the probability for a new customer to come in. Okay, waiting time does not affect the probability for a new customer to come. That's the meaning. Okay, so if you have been waiting for 10 minutes, the probability of customers to come in will remain to be the same, will not be affected by the time you have been idle waiting for the customers. So this is an example from machinery, electrical equipment, that for it says an old part is not any more likely to break down at any particular time than a brand new part. That think, for instance, if you have some equipment, the old one and the new one, okay? If you have installed the old machinery part and working, it does not necessarily mean that if you bring a new one, then the old one will break before the new one, or the new one will last longer than the old one. Okay, the events are independent; they don't depend on each other. The probability for the old machine to break will not be affected by the new one. Okay, here is an essay that the part stays as good as new until it suddenly breaks. So that is the memoryless property of an exponential distribution. Perhaps I take you through an example so that you can understand what we are speaking on. Now, if you do remember, we had an example, example 1. If you refer back to our previous example on exponential distribution, it was speaking on customer, the post of credit, the time is spent in serving the customers. So this is a continuation that, for example 1, where the time for post of clerk with his all customer has an exponential distribution with the mean of 4 minutes. This was the mean of 4 minutes. Suppose a customer has spent 4 minutes with a post of clerk. Okay, a post of clerk is serving customers. Now the average serving time is 4 minutes. That was the question. Now it says, suppose the customer spent 4 minutes with the post of clerk, then what is the probability that he or she will spend at least an additional 3 minutes with the postal clerk? Okay, we know the average time for serving the customer is 4 minutes. That's the average for 4 minutes. That is the average time for serving the customer. Now the question says, suppose you have spent 4 minutes with the customer, then what is the probability that you will spend some more minutes, some 3 minutes more? What is the probability? That is the question. So this one follows under the memoryless property of exponential distribution, that the probability of saving the customer 3 minutes more, given that you have saved for 4 minutes, will be the same as the probability of saving the customer for 3 minutes. That is the point. It says probability of saving the customer for 4 minutes, that is R plus T3, given that you have been saved for 4 minutes, will be the same as the probability of saving the customer for 3 minutes. That is the meaning. Now let's see how it works. Let's go to the example. This is example 2. Refer the example 3. Suppose that the part has already been just 15 years. The probability for that is just another 17 years. Now, these are the 2 examples. Now, let us see the solution and see for one example so that you can be in a position of solving some questions. I think I have the answers right here. Yes, here it is. That refer to example 1, where we spend the customer for additional distribution of the mean of 4 minutes. Suppose the customer spend 4 minutes with the postal clerk. What the probability that he or she will spend at least 10 an additional time of 3 minutes with the postal clerk? Now this is the question. So let us remind ourselves what was example 3 meant. Here, this was the cumulative density function for that particular problem, and this we are asked to find the probability that x is between 4 to 5, that the customer spends 4 to 5 minutes in saving the customer, and this was the result or the answer for that particular problem. Now this is not our concern. We are trying to remind ourselves what was that example 1. It was finding the probability that the cast time will be saved between 4 to 5 minutes. Now let's go back to our problem. Now in order to solve our problem, we have to remember the memory property, that the probability of x greater than r plus t given x equal to r will be equal to this much. It's the same as just calculating the probability of x greater than how much? T. That's the point. So the probability that the customer will spend at least additional 3 minutes with the postal clerk, given that he or she has spent 4 minutes, you see, with the postal clerk, can be written mathematically as, so 4 is r, 3 is our t. So it will be r is 4, this is t. So it will be 4 by 3, given that x equals to how much? To r, greater than r, sorry. This equals to probability of x greater than 3. Okay? Equal to probability of x greater than how much? Greater than 3. Okay? Now, how it is? So 4 by 3 equal to 7, it is this one. Given that x greater than 4 equal to p of x greater than 3. So in other words, for us to know, to find the probability that the clerk, so the postal clerk will spend additional 3 minutes, given that he has spent 4 minutes saving the custom, is the same as calculating the probability for x greater than how much? Greater than 3, only that. Okay. So defer the cumulative density function for our example. This was the cumulative density function. Average of 4 minutes, it is this one. Now, if we substitute x equal to 3 right here, we have the value for f of 3. Okay. If you draw it, we sketch this, it's like this. Here is an exponential function. And these are the x values. Let's say x equal to 3. This here, x equal to 4, and so on, all the way up to that point. So what we said is the exponential distribution, the cumulative density function of the exponential distribution gives the area to the left. So if x equal to 3 right here, if we substitute x equal to 3 in this equation, we'll have the area to the left of 3. So we will have this area. We will have, let me take this, we'll have this area here to the left. Okay, that will be x equal to how much? X equal to 3. Let me change the color for this one. Let me take this. Yes, I think this one can be there. Okay, we have this area right here. This is the area x equal to 3, the cumulative density function for x equal to how much? To 3. Now our aim is to find the probability of x greater than how much? X greater than 3. So this is less. So to have the probability for x greater than 3, it is from this point going this way. We have to take 1. We have to take 1, then we subtract the area to the left, this part here. We take 1, we subtract the area to the left. Area to the left is this point here. This is the area to the left of 3. Meaning that the same as taking 1 minus the cumulative density function of how much? Of f of 3. So equal to 1 minus how much? F of 3. That's the meaning. Now let's start by by finding f of 3. So from this one, we have f of 3. If we substitute x equal to 3, for x equal to 3, we have 1. This 1 is the same as this one, minus e to the x, it is 3 times 1 over 4. So we have substituted x for 3, and this is 0.5276. that is f of 3, or the cumulative density function when x equal to 3. In other words, it is the area to the left when x equal to 3. Okay, if I sketch here under figure right here, if this x equal to 3, then this area, the one to the left, is how much? This is 0.552. Okay, 527. That's our area. Now, our aim, yes, this is 3. Our aim is to have the probability for x greater than 3. So we know there's also area equal to 1. So if this is x equal to 3, then to get the area to the right, we simply take 1 subtracted by this, which equal to 1 minus this value here. So probability of x equal to greater than 3 is the same as 1 minus probability of x, or this should be less. Sorry, this should be less than 3. Okay, it should be less, not greater. It should be less than 3. Now, if we substitute these values, we have 1, it is this one. Then minus the probability of x less than 3 is the same as f of 3. It's the same as this thing right here. And what's the f of 3? F of 3 is this one. Okay, so if we subtract, we have this, and which is the required probability. So this one, the probability that the customer, the seller will have to spend some monthly additional minutes in saving the customer. Okay, this is a simplified one. Okay, it's the same thing but gives the same information, but it is more simplified. That probability of x greater than 3, which is what we need, equal to 1 minus f of 3. Okay, f of 3. Now this is 1. F of 3 equal to how much? F of 3 equal to this. So we can simply substitute 1 minus this much. Now 1 goes away. This one goes away with this. So we remain with e to the power 3 1 minus 1 over 4, which is give the same information. Okay, so that's what I'm saying. Probability of waiting for, you have spent 4 minutes, then addition of 3 minutes, given that you have been waiting for 4 minutes, this will be the same as the probability for the meaning. So this is an example on how to apply some problem relating to exponential distribution that follows the memoryless property. We have some other example right here, but I can leave this for you to solve and see what you come up with. If you want to know the data, what were the results, you can go back to example 2 in the previous video. Then we find how was this question, and you have the result set for you. So know that you have the information for question 2. Then you can come up with the required probability. Thank you for listening, and join me in the next session. We shall be discussing about gamma distribution. Thank you.